looking at stereochemistry, we talked a little bit about different types of isomers. So in general, an isomer is something that has the same chemical formula but different structures. And so really we split isomers into two things. We split it into constitutional isomers and stereoisomers. So constitutional isomers and stereoisomers are two different things. Constitutional isomers, the atoms are connected differently. All right, so we could add here different connectivity. So that means that maybe instead of the bromine being on the second carbon, it's on the third carbon. They still have the same chemical formula, but the atoms are actually connected in a completely different way. So those are constitutional isomers, right? Atoms with the same formula, but the atoms, or molecules with the same formula, but the atoms are connected differently. Then we get into stereoisomers. So we've actually already talked about one type of stereoisomers when we've looked at cis and trans. So a stereoisomer has the same connectivity, it's just different spatial arrangement. So same connectivity. All right, I'm gonna actually put spatial arrangement just so that we know that it's not like arrangement, like the connections. So remember when we did cis and trans, we looked at the chair conformations. Cis was when you had the substituents on the same side of the ring. Trans, they were on opposite sides of the rings. So cis-trans isomers, the atoms are connected in the same way, it's just they're arranged differently in space. And then another type of stereoisomer are isomers that have asymmetric centers or chiral centers. So we'll look at chiral molecules a little bit as well. So that's just going back and kind of looking at isomers. We've talked about different types, but we're going to kind of focus on one specific type of stereoisomer, which is looking at chirality today. With those isomers, we're going to be looking at the enantiomers, and then we'll talk tomorrow into the end of the week about diastereomers as well. So just a couple of different types of additional isomers as well. So with chiral objects, we've talked about both of these a little bit. A chiral object, or even a chiral molecule, right? Anything that's chiral has a non-superimposable mirror image. Superimposable means you can lay it on top of each other and it's the exact same thing. And so our right hand and left hand are mirror images of each other, but I cannot rotate one of the hands in a way that I can lay it directly on top of the other hand and it's the exact same. It shows some other examples as well, right? Like an ear is the same way. Achiral has a superimposable mirror image. So look at the example of the fork. You have the mirror image. I could move the mirror image over and lay it directly on top of the other fork. It's the exact same thing. That's achiral. So its mirror image is not different from the original object. So that's looking at chiral versus achiral, looking at the mirror images. Sometimes you have to look at, like, how can I rotate? How can we rotate a molecule to see if it's the same thing? So it becomes some visualization as well, which for some people might be a little bit difficult, but that's why we have the model kits as well. So in the activity that we actually did last week, we looked at capital letters that were chiral and capital letters that were achiral. Achiral just means not chiral. So that means chiral, the mirror images are different. So I did an F, for example. I showed the mirror image of the F. There's no way to rotate this mirror image to be able to lay it directly on top of the original letter. If I were to try to rotate this, I try to rotate it 180 degrees, it'll look like this, and I cannot move this and lay it directly on top. This becomes a different object from the original. When you're trying to superimpose it, you're not taking the mirror image again. You're looking at can it rotate in a way. So this just shows examples of capital letters that are chiral, so their mirror images are different, and then the capital letters that are achiral, their mirror images are the exact same. So like the letter M, I can just move this over, lay it directly on top. It's the same thing.
So like K, like when you like do the like a transverse, it looks different, but you can rotate.
It. Yes. Yeah, if you can rotate the mirror image, so you're just kind of twisting it and turning it, then you can do that. If you have to flip it again to make it the original, then it's chiral. Yep. Okay, so then to look at asymmetric centers. Now, asymmetric centers are the same thing as chiral centers. So a chiral molecule has what's called an asymmetric center, or we are just going to call it a chiral center. Right, so a chiral center. This is an atom that's attached to 4 different groups. That is really, really important. It has to be 4 different groups. Now, almost always when we look at these chiral centers, because we're dealing with organic, it's going to be a carbon. So almost always it's going to be a carbon, but because it's attached to 4 different groups, it's sp3 hybridized. Now, that's when we went back and we looked at shapes, but what that means is that there are 4 substituents attached to that carbon. So a carbon that's in a double bond cannot be a chiral center. It doesn't have 4 different groups. It would only have 3, or maybe 2 if it's double bonded on both sides. So you're looking at a carbon single bonded to 4 completely different groups. It shows an example here of 2-bromobutane. All right, so here's a carbon. It's attached to a hydrogen, a methyl, an ethyl, and a bromo. Those are 4 different groups. So this carbon, right, this central carbon here, is a chiral center. It has to be attached to 4 different groups in order for it to be a chiral center. If you have 2 hydrogens, it's not a chiral center. So if instead of CH3 this was a hydrogen, it can't be a chiral center because that carbon is attached to 2 hydrogens. So it always has to be 4 different groups in order to be a chiral center. So this shows a couple examples, and you have this kind of in the notes on the slides as well. So for octanol, when you are looking at what it's attached to, you are looking at the entire group that the carbon is attached to. You're not just saying, oh, well, this is attached to a CH2, this is attached to a CH2. You want to look at the entire thing. This carbon has a propyl group on one side, and it has a butyl group on the other. Those are 2 different groups. Right, then there's the hydrogen, and then there's the OH. So that carbon is attached to 4 different groups. That makes that a chiral center. This is just the same thing. It just shows it as a bond line structure to make it a little bit easier to see. Sometimes people like seeing that bond line structure instead. Here's that carbon. So 1, 2, 3 carbons attached to one side, 4 to the other. There's always a hydrogen here, because there has to be 4 connections for a single bonded carbon, and then you have the OH at the bottom. So when it's attached to 4 different things, it's a chiral center. So just showing some examples of the chiral centers there. All right, here's another one that shows dimethylhexane. So here, you're looking at the entire thing that it's attached to. So on this side, and it kind of explains it here, you have a hydrogen, there's one group. You have an ethyl, there's another group. You have a methyl, there's a 3rd different group. And then over here, you notice you have 4 carbons attached, isobutyl on that side. As long as it's 4 different things, I'm not asking you to name this, I'm asking you to find chiral centers. So find, is there a carbon that's attached to 4 different groups? 2,4-dimethylhexane has a carbon attached to 4 different groups. Now what I'm going to do is I'm going to show you another one. Right, this is actually the bond line structure of 2,4-dimethylhexane. This is the chiral center that's attached to 4 different things. Now we also have a carbon, right, that some people would look at and they'd say, well, why isn't this a chiral center? This is attached to 4 things. Well, this carbon, yes, it's attached to 4 things. Right? You have this whole group over here. It's attached to this entire thing. But here is a CH3. Here's a CH3, and then you always have a hydrogen off of it as well. So this entire group and the hydrogen are 2 different substituents. Then you have a methyl, that's a 3rd different substituent, but the 4th group that it's connected to is another methyl. These 2 are not different. So that's not a chiral center. So not a chiral center because there are 2 methyl groups. Since those CH3 groups are not different, that carbon can't be a chiral center. So when you're looking at chiral centers, you are looking at where are there 4 different groups connected. If they're not 4 different groups, can't be a chiral center. All right, so that was a little bit, and I know you were looking at chiral centers in the activity as well last week, but just kind of looking at some different examples and then why we might have something that's not a chiral center. Now, kind of as we continue to look at chirality, so chiral compounds have, again, you're going to see that word non-superimposable mirror image. That means the mirror image is not the same. Right? The mirror image is different. They are not identical. Achiral have superimposable mirror images. That means they're identical. The mirror image is the exact same thing as the original molecule. You're just rotating it. Biggest thing with achiral is that you can rotate it to make it the same thing. Now you have some, and by some I mean 1, right, kind of key term up here. Enantiomer. An enantiomer is the mirror image of a chiral molecule. So it's like you say that, 2 people are twins. So one person is the twin of another. It's the same thing with enantiomer. This molecule is the enantiomer of this molecule. This molecule is the enantiomer of this molecule. So you have enantiomers of each other. Now, every molecule can only have 1 enantiomer. Right? Just like one person can only have 1 twin. Because you have more than 1, well, now it's no longer twin. So molecules could have 1 enantiomer if it's chiral. And the reason that this is chiral is there's no way that I can rotate this. Think about if I just take the bottom of this molecule and I try to rotate it. So right now the hydrogen is back behind, right? It's going into the page. If I try to twist it, so I twist it just a little bit. Well, now the ethyl is going to go back into the page, the methyl is going to be off to the side, and the hydrogen is going to be out front. There's no way that I can rotate this to make it the exact same thing as this. So they are enantiomers of each other. Now here's another one, because there are 2 hydrogens here. Here's the mirror image. So then you want to see, okay, is there a way that I could rotate this? So I take the bottom of this molecule and I rotate it. So I kind of rotate it 2 times. 1, the ethyl becomes a wedge. Right? The second, it's going to come over off to this side. And then I'm going to have the 2 hydrogens over on this side. Then I can move it over. I can lay it directly on top. So you either have enantiomers or identical molecules. If a molecule is chiral, it has an enantiomer. If it's not chiral, the molecules are identical. So you just have to look at, can you rotate the molecule? If you can rotate it and just lay it directly on top, it's going to be achiral, right? Not chiral. So kind of looking at enantiomers a little bit more, the definition of an enantiomer is that it's a mirror image of a chiral compound. Shows right here are 2 stereoisomers of 2-bromobutane. So here's the mirror. A mirror image, you're just taking everything you see and just drawing the reflection. So the hydrogen is on kind of closest, still a dash, methyl still a wedge, ethyl still off to the side. You look at, can you rotate it? If it's a chiral, right, a chiral center, it's probably a chiral molecule. Right? If you have a carbon that's connected to 4 different substituents, it's probably going to be a chiral molecule. So these two isomers are enantiomers. They are different compounds, and we're going to actually look at how the naming is just a little bit different, probably towards the end of the week. So even though they are isomers of each other, they're stereoisomers. They have the exact same formula. They're just arranged in space differently. Kind of like with double bonds, we use E and Z. With these enantiomers, we're going to look at how to name these using R and S. So the naming will actually be a little bit different. It's still 2-bromobutane, but we're going to add an R or an S at the beginning to show how they're arranged in space a little bit differently. But you can actually separate these, and we'll talk about racemic mixtures, which is when you have a mixture of these enantiomers. So this is kind of a little trick for enantiomers. You can actually draw enantiomers by switching the two groups on a chiral center. What we mean by switching is taking the wedge and making it a dash, and taking the dash and making it a wedge. And when you were doing that activity with the models, it had you actually switch the positions of two of the atoms. It had you do this. And so when you actually know, all right, I know here I have a chiral center. How do I know? Well, I have a methyl, I have a fluorine, I have a hydrogen, and I have an ethyl. 4 different groups. This is a chiral center, which means this will be a chiral molecule. A little trick for if it says draw the enantiomer of this chiral molecule, just make the wedge a dash, make the dash a wedge. There's your enantiomer. You can actually just switch the wedge and dash, and it makes it into the enantiomer. Because this, you had a mirror image, this is rotated to make it kind of look to the similar structure. Having the ethyl on one side, this is rotated, but if you switch the wedge to become a dash, the dash to become a wedge, these two are enantiomers of each other. These are the mirror images of each other. One might be rotated, but they're still the enantiomers because the wedges have become dashes, dashes have become wedges. Now, this is kind of tying it more into bio. I'm not getting into this a whole lot because I don't teach bio. But here's kind of the difference between, I said that we name it using an R and S. This just kind of shows kind of a biological example where you can have receptors and you have chiral molecules that only one of the enantiomers can work. And I'm going to show some actual examples. And yesterday in the reading, you read about some examples. You read about how some of them smell differently. Some of them are fatal. Right? You could have the R, which is fine, and the S, enantiomer, can be fatal. So the R and S, we do distinguish them. Right? And this kind of shows the example of you have the R that will fit into the receptor just like it's supposed to, but the S enantiomer, when it's rotated, right, it's the mirror image now. Well, now there's no way, no matter how I rotate this, because they're arranged in space differently, no matter how I rotate the bottom of this, there's no way that I can make all 3 of those substituents fit into the receptor like they need to. So that just kind of shows how the R and the S, even though they have the same formula, they're connected the same way, because they're arranged in space differently, they are different enantiomers, right? They can have different properties. So just kind of showing that biology. So there was an example of this, oh gosh, we did the article a while ago, on thalidomide, when there was the R and the S enantiomer of thalidomide. The R enantiomer is a sedative. So the R enantiomer, right, is to help calm, right, whatever you want to use a sedative for. And then the S enantiomer is actually what was given to women, and it disrupted the development of the embryos, and then a lot of kids were born with like developmental disorders, right, or their bodies just didn't develop like they needed to. So that's the difference here between the R enantiomer and the S enantiomer. Right? One is just to help calm you down, and the other one ended up completely disturbing women's pregnancies. So the physiological properties are a little bit different. So this is just showing right here the different, here's a chiral center. You have one substituent, right? You have this side of the substituent, this side of the ring is different, and then you have a hydrogen. So thalidomide is one example of an enantiomer. This also is showing, right, the difference between Vicks and meth. Right? Like, here's an actual real-world example of the difference between a wedge and a dash. Notice the only difference here is that the methyl group here is a dash. The methyl group here is a wedge. So these are enantiomers of each other. This is the active ingredient, right, in Vicks. So you're sick, you put Vicks on your chest or feet or wherever, versus, oh, look, we made Vicks wrong. So, right, the methyl group with a wedge instead is methamphetamine.
Nice. That's so funny.
Right. Welcome to Organic Chem. So here's another example. And this isn't as different, right? We're talking about oranges and lemons here. But still, right, the difference, you have the plus, which we'll talk about when we talk about optical activity, found in oranges, the minus found in lemons. Now, both citrus, so again, not as drastic of a difference. But these two are enantiomers of each other. Right? So a lot of times their physical properties are similar. Melting point, boiling point, that'll be the same. The physiological properties, though, right, how they affect you, are different. Vicks will affect you a lot different than meth. Okay, so here is just kind of some practice. Work with a small group, people around you. All I want you to do is identify if the following compounds have an asymmetric center. Do they have a chiral center? If so, identify that. You can put a little star next to it. All right, so for example, if you see in this first one, if you notice that it has a chiral center, just put a little star next to it. Remember, you're looking for 4 different groups. And sometimes what you'll notice that I do is I'll start like underlining, and I'll do different numbers of underlines for the different numbers of groups. All right, something like that. So this one has 4 different groups attached. That carbon is a chiral center. What about this next one?
No.
Why?
Because it's CH3 and CH3.
Right? 2 methyls. So this is not a chiral center. Right, this one.
Yes, sir. I'm just kidding now. I wrote
Right, this one's not.
I wrote now. Don't worry.
Because there are 2 ethyl groups on each side. And then this one, right, yes, you have 4 different substituents. You have a methyl, you have an ethyl, you have a propyl, and you have a bromo. So when you are looking at chiral centers, you are looking at where are there 4 different groups attached to a carbon. And maybe, like some of these, there aren't any. Now, let's see if we can look at this.
Okay.
So this is an antibiotic. Right? Antibiotics have some complicated structures. Now with this, remember, it needs to be a carbon attached to 4 different things. So carbons that are in double bonds cannot be chiral centers. So none of these can even be chiral centers. Right? This carbon can't be a chiral center. It has a double bond attached. Right? These, they don't even have the potential to be a double bond or to be a chiral center. So any place that there's a double bond to a carbon, it doesn't even have the potential to be a chiral center. Now, you can look at some of the other ones and see, okay, now we know we have these single bonded carbons. Now, the question is, are they attached to 4 different groups? When it comes to rings, you want to look at, so like this carbon, for example, we see it's attached to a methyl, a hydroxyl, which is OH, and then you want to look at what else it's attached to. This is attached to a carbon, right, which is also double bonded to something else and single bonded to something else. This is attached to a carbon, right, that's single bonded. So these are 2, basically you're asking, do these sides of the ring look different? Right. Yes, that's a chiral center. So that's kind of the question that you want to ask yourself as you look through. Do each side look a little bit different?
Before we started this, she would say like chirality. She would say chirality. I was like, what? The fire? I was like, what?
So there should be 1, 2, 3, 4, 5. Yeah.
Okay. What? Oh, yeah.
Now, this one is not. Why is this not a chiral center?
There's 2 H's.
2 H's. So it doesn't even have the potential. Well, I mean, I guess it does have the potential, but it can't be because it has 2 groups. Now, when it comes to looking at how many stereoisomers we could have, all right, when it comes to how many stereoisomers could we have? All right, possible stereoisomers. We have 2 to the n. So if we're looking at like how many combinations do we have of like wedges and dashes, right? We could make one substituent a wedge, one a dash, and then the other 2 are in the plane. If you're looking at the possible combinations of stereoisomers, it's 2 to the n. And then n is the number of chiral centers. So here we have 5 chiral centers. So if we're looking at how many possible stereoisomers do we have here, 2 to the 5th.
32.
Okay, there we go, 32. Right, 32 possible stereoisomers. The biggest thing is just it's 2 to the n. If you know how many chiral centers there are, you can figure out how many possible. Am I going to ask you to draw all 32? No.
Dang, I really
Right.
wanted to.
But it's good that you know how many possible you could have. So then just a quick kind of more of a terminology type thing is an asymmetric center. That's a chiral center. So asymmetric center is the same thing as a chiral center. The difference between a chiral center and a stereocenter. Now, this is like all thumbs or fingers. Not all fingers are thumbs. Is that the right saying? Something.
Sure.
Okay. A chiral center is also a stereocenter. So, an asymmetric center, right, a chiral center, so again, see chiral, is an atom that's attached to 4 different groups. All right, we just looked at that. A stereocenter is an atom where if you switch 2 groups, you produce a stereoisomer. Now, notice a chiral center is also a stereocenter. A chiral center is also a stereocenter because if I switch 2 of these, right, if I switch 2 of them in space, it's a different, right, it's an enantiomer. It's a stereoisomer. Now, here we also see it in a double bond. This is why Although all chiral centers are stereocenters, not all stereocenters are chiral centers. Because when you look at this double bond, this is where we're going back to, all right, cis and trans. These two substituents are on the same side of the double bond. Right now, these are cis. All right, this is a cis double bond. If I switch the hydrogen and the methyl, right, it's still connected the same way. Right, I still have a hydrogen and a methyl connected to that carbon, but now if the methyl's on the other side and I switch it, then it becomes trans. Remember, cis and trans are stereoisomers as well. So a stereocenter is where if we switch two groups, switch two substituents, you're creating a different stereoisomer. This cannot be a chiral center, though, because carbon isn't attached to 4 different things. So that's looking at chiral center versus stereocenter. Now, very quickly about racemic mixtures. All right, we're not going to get into like the full process of separating them, but a racemic mixture is a 1-to-1 ratio of both enantiomers. All right, a racemic mixture is a 1-to-1 ratio, a 1-to-1 mixture of both enantiomers. So here we're going to talk more about what it means for something to be left-handed and right-handed. But we have the left-handed crystals, the right-handed crystals. A racemic mixture has a 1-to-1 ratio of both of those. Now, one way that we can separate racemic mixtures is through chromatography. All right, this is column chromatography, which is a little bit different than paper chromatography that we did last year. But you can separate because they're going to have slightly different polarities. All right, so you can actually separate them using chromatography. But the biggest thing is a racemic mixture is just a 1-to-1 ratio of both enantiomers. Some over-the-counter prescriptions, or no, wait, just over-the-counter drugs, because they're over-the-counter, not prescription. Like Advil, ibuprofen, those are actually sold as racemic mixtures. So you actually have a mixture of 2 enantiomers, because a lot of times you're going to notice on the back of the label it says that one of them is inactive. So it's actually easier to sell a racemic mixture than it is to try to separate them out when one of them is inactive anyways. So just kind of some examples. So the last thing that we'll probably talk about today, and then we'll finish this up tomorrow, is plain polarized light. Now I'm going to talk a little bit about what plain polarized light is, and then I'll tell you really what you need to know about it. So, normal light oscillates in every direction, right? You see light as just kind of a, there it is, right? Plain polarized light is when you put it through a polarizer. It actually just shines in a single direction. So you have a light source, normal light's just going to shine, you put a polarizer here, and then it's actually just going to shine in a single direction. This is plain polarized light. Now, how it relates to chiral molecules is that an achiral compound, so something that's not chiral, is optically inactive, which means we have this plain polarized light. It's shining in a single direction. Here's a sample that has an achiral compound. The light is still shining in the single direction. So an achiral compound, if you're not sure if something is chiral or not, you can actually shine light through it. Right? You can see if it rotates the light. A chiral compound is optically active. So a chiral compound, you do the same thing. You have the polarizer, here's the polarized light. You continue to shine that polarized light through the sample with a chiral compound, and what actually happens is that it slightly rotates the light. So now the light is shining in a rotated direction. Now here's really one of probably the bigger things. This is where that plus and minus came in. If it rotates the light clockwise, you'll see a plus in front. If it rotates the light counterclockwise, you see a minus in front. So you still have the enantiomers, right? And we noticed with the example before we had the plus and the minus. So one enantiomer will actually rotate it clockwise, the other will rotate it counterclockwise. All right, so here's going to be kind of just summarizing what happens with optical activity. So a chiral molecule will rotate it at some angle, right? And that is given by the symbol alpha. Its enantiomer will rotate it the same angle, but opposite. So notice it's A, right? It's alpha and negative alpha. So chiral compound will rotate it a certain way. Its enantiomer just rotates it the opposite. Achiral will not rotate it. A racemic mixture also will not rotate because you have positive alpha and negative alpha. They just undo each other. So really we just see that rotation with the chiral molecule and with its enantiomer. So this gives this equation, yeah, we're not worried about this equation, right? They can calculate the rotation. They could calculate the wavelength, right? They could calculate different things using optical activity. But then this is just showing the last example of the enantiomer, right? If one is positive, one rotates it positive 5.75. Its enantiomer rotates it negative 5.75. So optical activity, you just have positive and negative.